Okay, let's take a classic example. Let's say that we have a function r of t, which is the position vector of some particle that's moving through space. So this is a vector. It has a component x, y, and z, and each of those separate axes has its own scalar function that tells us where that particle is going to be. If we were to take the derivative of this, the derivative of position, okay, this obviously is going to be dr dt, but it's also going to be equal to velocity at time t. This velocity, though, is a velocity vector. This is a vector, this is a vector. What are the components of this vector? Well, it's the velocity in the x direction, the velocity in the y direction, and the velocity in the z direction. Okay? And that's because we just took the derivatives of the velocity of the position in the x, position in the y, and position in the z, and obviously that's what we're going to get. So we can say velocity is equal to the derivative of the position vector over time. Speed is simply the magnitude of the velocity vector. And if we want acceleration, okay, that's equal to, you can think of it in two ways. It's either the second derivative of the position function with respect to time, or alternatively, it's the first derivative of velocity. That's going to be exactly the same thing. Okay? And finally, if you want to have a unit direction vector for the object at some time, it's simply going to be our velocity vector divided by the magnitude of the velocity vector. We're used to seeing that before. And yeah, I think that's pretty much it. The last thing we could do is, and this seems pretty obvious, we talked a little bit about it last time, if we take the unit direction vector times the speed, this is equal to velocity, obviously, right?